Hi everyone, so in this video we're going to take a look at the concept of isotopes of an element. And we're going to use this diagram from the mineralogy textbook by Klein and Dutrow, where it's nicely diagramming isotopes of carbon and nitrogen and oxygen. So for the carbon example, all carbon has 6 protons in the nucleus, and they're showing that here. The authors are showing the protons as small black dots. We add them up, 6 black dots over here for carbon 12, and then the same number for carbon 13. The 6 itself is redundant. As soon as we write the letter C, then by definition we have to have 6 protons in the nucleus. If we do not, then we do not have carbon. We must have some other element. For example, if we have 7 protons, then we have the element nitrogen, which is shown down here. However, while the number of protons is fixed for each element, the number of neutrons is not. So over here, we have 6 neutrons. So 6 neutrons and 6 protons gives a total atomic mass of 12. Here, though, we have 7 neutrons. So 7 neutrons plus 6 neutrons gives us a total atomic mass of 13. So we have carbon, and it will act, this carbon 13 will act exactly the same way as carbon 12, and it bonds to other kinds of things. So if we make carbon dioxide, when oxygen bonds to carbon, as we'll see later, it doesn't care whether it's bonding to carbon 13 or whether it's bonding to carbon 12. It'll still form the same kind of bonds. The bonds will be very similar, almost identical in strength. We'll see a little bit of variation in that in another video, but we can eventually, for our purposes today, we can just consider them the same. And the same is going to happen for these other elements here. So they are illustrating nitrogen 15 here, which by definition must have 7 protons in the nucleus, and then nitrogen 14 on the left. So this nitrogen will react with other compounds or react with itself to form, let's say, molecules of N2. But those nitrogen atoms that are bonding, they could have a weight of 15 or 14. In terms of the chemical properties, it's not really going to matter. And then oxygen, here they're illustrating 3 isotopes. There's oxygen 16, oxygen 17, and oxygen 18. Now, by virtue of the fact that we've written oxygen here as the elemental symbol, it must mean that we have at least 8, well, not at least, but exactly 8 protons. Let's fix that up a bit. We must have exactly 8 protons in the nucleus. But we could have as many as 6 or 7 or 8 neutrons in the nucleus, which changes the atomic weight. So when you drink a glass of water, that glass of water is probably going to be mostly H2O16, but some of it might be H2O17 and some of it might be H2O18. You can drink that glass of water with any number of those isotopes. None of them are radioactive, so it won't really matter to you. This is just a little bit heavier than this guy, but it'll work the same way. If you're worried about being hydrated after a workout, you can drink any of these and you will be just fine. Your body will treat it the same way. It doesn't know and it doesn't care. So the way it works in both chemical reactions and biochemical reactions, it's all going to be the same. However, there are some subtle differences between oxygen 16 and oxygen 18 in the way they evaporate from seawater. And in a later video, we're going to take a look at the isotopic fractionation, how these isotopes can be separated from one another, and tell us some really interesting things about climate.